Math 3 Lesson Summary Video, Segment Lengths in Circles. This lesson is a Develop Understanding task, which is meant to introduce you to a concept, but not necessarily finalize all the rules or strategies. The purpose of this lesson is to make observations about the relationships between segments created in and around a circle by chords, secants, and tangents. In each of the circles below, two chords are intersecting in the circle. For each figure, measure the lengths of segments AE, BE, CE, and DE in centimeters and record in the table. You may also use dynamic software to create and compare measurements. After I measured the first circle, I got the following measurements. What I want to look for are patterns to see if there's any relationship between these segments. I just have to start by trying something. I think I should probably keep my pieces of the same segment together. So for example, AE maybe should stay with EB and CE could stay with ED. I'm going to start by adding. So if I take 1.9 plus 3.1, I get 5. 2.2 plus 2.65 is equal to 4.85. Close, but not congruent. So let's try subtraction. 3.1 minus 1.9 is 1.2. And 2.65 minus 2.2 is 0.45. Definitely not equal. After addition and subtraction, our next option is multiplication. So 1.9 times 3.1 is 5.8. 2.2 times 2.65 is also 5.8. So that's interesting. It would appear if I take this piece times this piece, I get the same result as when I take this piece times this piece. If you don't know, when you have two things times one another that are equal to each other, that's a proportion. And so we've set up an interesting proportion. We're making a conjecture that if I take the two pieces of a chord, because when these intersect inside the circle, each chord is cut into two pieces. We don't know that those two pieces are congruent, but what it appears to be is that if we multiply those two pieces, they do have to be equal to each other. So if I take a piece times a piece, as long as they are the two pieces from the same chord, it's going to be equal to piece times piece. Both of the pieces from the other chord. So when we multiply them, they actually end up being equal to one another. This seems like it'll be useful because if I know 3 of those pieces, but I don't know the 4th, I should still be able to plug in and find that missing piece. The following series of diagrams shows two secants intersecting outside a circle. Various segment lengths and products are shown. Analyze the diagrams and look for relationships between segment lengths and/or products. Note, R indicates the length of the radius of the circle. Now here, it also looks like they've already given us the measurements for different things. They found the measurement of AC, of CP, of AP, the whole thing. They found all the little pieces BD and DP and BP. And then they've also taken all of these little segments and they've multiplied them times each other. And when we're looking at those patterns, I notice that I have an 86.61 or 86.1 here and an 86.1 here as well. That's the only place that I find that they are overlapping, that they're exactly equal. I find that those two pieces that are equal to one another, anytime we know things are congruent, that's powerful because we can set up congruency statements. Let's look at the pieces that we're dealing with. We're talking about CP in relationship to AP. And then we're looking at DP in relationship to BP. Now, if we could kind of sum up what those pieces were, it looks like on this secant, I'm taking the outside part of the segment and I'm multiplying it times the whole segment. So the outside piece times the whole thing. And when I do that, it is equal to, on this secant, it is the outside piece, and it's getting multiplied times the whole thing. Again, if we can set that relationship up, plug in what we know, we can always solve for a missing piece of that puzzle. The following series of diagrams show a secant and a tangent intersecting outside a circle. Various segment lengths and products are shown. Analyze the diagrams and look for relationships between segment lengths and/or products. So just like the last problem, we want to see if anything is actually equal or if we can make things equal. I notice the 4.9 and the 4.7 are close, but not quite there. I do see, however, 22.3 and 22.3. So if these two things are equal to each other, we have BP times AP, and it's actually equal to CP squared. Let's look at our picture and see what that is. BP is this outside piece of the secant. AP is the whole thing, the whole secant. Well, that's just like the last problem. CP, though, is just the tangent. It's the whole tangent. It goes from the point to the point of tangency. It is just the tangent line, and it happens to be squared. So this looks like it's a whole new formula. But I can make a connection to it in the last one. If you notice the tangent, CP, similarly to BP, is the outside piece. This segment never goes into the circle. So it is still the outside piece, and it is still being multiplied by the whole piece. It's just that in a tangent line, the outside piece is the whole piece. And anytime you multiply something times itself, it gets squared. And so that's where this relationship comes into play.